Yeah, so we'll start out today trying to get back in the groove of what we were doing a little bit. What we were talking about on Monday, when we were last doing fluids and not a test, we were talking about what we call the Navier-Stokes equations. So this is right from chapter 5. We looked at the Navier-Stokes equation. We went through that whole handout and had an equation. I'll just write the X part of it. Right, you have this equation in your handout. Plus V dy plus u du dz equals, so right, this is that's the acceleration of our particle. That's mass. That equals the sum of all of the forces that are acting. So equals rho g minus the pressure dx plus mu d squared u dx squared plus dy squared d squared u dz squared. So this is gravity. Pressure. And viscosity. So we derived this equation in a fair bit of detail. This is just the x direction, right? So we'd have to, have a y direction and a z direction. That would be able to cover F equals ma, right? This is forces acting on our little fluid particle. This is F equals ma for our little fluid particle moving in some sort of velocity field. And when we derived this equation, when we went through that worksheet and looked at kind of where all these parts come from, right? It's big and it's ugly, but it's nice to, I think, at least try to get some idea of what the different pieces of the equation are. So it's not just this big ugly piece of math, but these are actually things that come from somewhere, and they're actually just like F equals ma. It's a really simple equation. This is built on assuming an incompressible fluid. So that's one of our core assumptions. So this whole thing assumes right? It assumes an incompressible fluid. But if you have an incompressible fluid, which nothing is perfectly incompressible, but lots of things are really close, then these are the equations that govern that. And we talked about, this is the reason that we went through this and derived it in detail is not because we're going to solve it a whole bunch. We'll do a little bit of that, but primarily because it's worth seeing where this comes from, because this is one of the most important equations in fluids, because this is how we look at fluid flow. How do fluids move if we apply some forces? We have forces on the right-hand side. We have how they move on the left-hand side. So it's a fairly important equation. What we're going to be doing today is taking a look at one class of, one kind of broader class of problems, and looking at some solutions, some concepts that we can take from that. And that brings us from chapter 5 to chapter 6. Which is incompressible inviscid flow. Inviscid is a fun word. Inviscid just means viscosity is 0. Inviscid, non-viscous, that's all that means. Right, sometimes we get to invent terms just because then we know what we're talking about and other people don't. So inviscid flow means that the viscosity is 0. If it's incompressible inviscid flow, that means it should be governed by the same Navier-Stokes equation here, except that viscosity is 0. We said this is nice because this governs a whole range of problems pretty closely. It doesn't cover anything exactly because viscosity is always something. Like it's never exactly 0. There is no fluid that has exactly 0 viscosity. But there are lots of things and systems where viscosity, viscous forces, right? If you look at this, this right-hand side of the equation here, where gravity and pressure are big and viscosity is small relative to those. So there are a lot of real-world situations where that's pretty close. So those are situations where, okay, what are the important forces? Gravity and pressure. Viscosity, not so much. It's always there in real life, but it's often often small. So very small, and this is relative to pressure gradients and gravity. So small is not, there's no absolute, but it's small relative to the other stuff, relative to pressure differences in the system, relative to gravity. You know, if you looked at the right-hand side, you know, the first term gravity is 100, the second term pressure is 10,000, and the third term viscosity is 4. Okay, well, that's pretty small. So that's kind of what we're looking for. We're looking for places where the other two terms on that side are significantly bigger. That happens a lot in aerodynamics or gas flow in general, because viscosities of gases are really small. It also happens over in liquid flows with large changes in pressure and or well, large changes in pressure, I'll write it this way, over short distances. So again, if kind of that pressure term is dominating, that's when this often is the case. If that's the case, then we get what we call Euler's equations. So this is basically Navier-Stokes if we set mu equal to 0. And I'll give just the x direction here because we already wrote all of these, but it'd be rho du dt du dx plus v du dy plus w du dz equals rho gx plus, or rather minus the pressure dx. Okay. In general, this is a kind of a more compact way to write it. D velocity dt, right, where this is our weird notation for the acceleration of a particle in that flow, the material derivative, equals rho g minus gradient of pressure. And I'll circle both of, or I'll box both of those. So this is like the expanded full version. The other one is the nice, compact, a little bit easier to write version in vector form. So it takes on whatever equations you, or whatever directions you might have in your problem. So the way that we're going to think about this is we're going to think about it for a relatively simplified case and try to, again, build some intuition about what this means for fluid flow. But what you can see already is, okay, so why in this kind of flow, why are fluid particles accelerating? Well, they're accelerating, that's this term, because of gravity and pressure gradients. So that's what's driving fluid flow. That's what's governing it. If we look at the simplified case, where we don't have the velocity field changing with time, so we have a steady state velocity field. So that would be right, the velocity field is equal to, the change in the velocity field with time is equal to 0. Then this was a system where, right, like path lines and streamlines and streak lines are all the same. So when you see like lines in your experimental fluid flow, those are the streamlines. So if this is the case, then we can look at the flow along a streamline, because that's right, particles are going to be moving down along a streamline. So we have some streamline there. Those are our streamlines. Right, these are not changing in time because it's steady state flow. We're going to be looking at a fluid particle as it moves along that streamline. And we're going to define kind of a weird coordinate system. We're going to give a coordinate system based on like the particle. And we're going to like attach axes, kind of like what we did when we were looking at like an accelerating control volume or a moving control volume. We attached axes to the control volume. We're going to do the same thing, and we're going to attach axes to a particle as it moves along our streamline. So we'll attach axes. There's going to be a normal direction. We'll call that N. There's going to be a direction that the particle is moving. We'll call that S. And there's going to be a direction like in and out of the page, which we can call X. So N is normal to our streamline. S is the streamline direction or the streamwise direction. X is in and out of the page. So our fluid particle is moving at that point. That's where the axes are going to be. As it moves to a different point, though, our axes are going to shift and move with it. So if we watched our particle, say at this point here, now our S direction, our normal direction is going to be pointing in that way. Our streamwise direction is now pointing down there, and X is still pointing in and out of the page, but right, that all rotates along with it. So our axes, we're going to attach them to this particle, and it's going to kind of shift and move as it moves through the flow. Okay. At every point, one of the reasons why we wrote the Euler equation like this up here is at every point that equation works. Okay, so the acceleration of the fluid particle is equal to rho g minus gradient p, like that works as our axes are moving. This equation still governs that. So if we look at the streamwise direction, S, we could write rho v dv ds equals rho g of s minus dp ds. Okay. This guy, g of s equals minus g partial z partial s. Right, this is like for our height changes. As it moves in S. So right, our little particle goes up and down as it moves along the streamline. So that's what this is capturing. Practically though, for a lot of flows, we don't really have to care. So we'll neglect it because it's typically not a particularly huge part of what our problem is. So we're going to neglect we're going to forget about that part because, right, especially if you're talking about like aerodynamics and flow of gases, gases don't weigh a whole lot. So that density term is pretty small. If you're talking about flows like from left to right, your height changes are not huge in those situations. So often kind of both of those terms are small enough that that's not the major component of what's happening. So this would be like small delta z, small density, then that works, okay. So what does this tell us? So this tells us So if rho GS is about equal to 0, if we do neglect that, then we have rho V dV ds equals minus dP ds. Or right, we can say V dV ds equals minus 1 over rho dP ds. Then let's look at what these terms are. So this is the acceleration of the fluid particle along the streamline. Right, so our fluid particle, and if we zoom out a little bit, so you can still read that, it's moving, our fluid particle is moving along the streamline, right, in, say, this direction. It's going to be potentially speeding up and slowing down, right? We kind of, by definition, it's staying along that line, but it could be speeding up or slowing down. Why is it going to speed up or slow down? It's going to speed up or slow down because of, this is the pressure gradient, right? So the fluid is going to be speeding up, right? Negative pressure gradient. So that means as pressure goes down, the speed goes up. As pressure goes up, the speed goes down. So the fluid will accelerate toward low pressure and slows down as pressure goes up. So you're picturing it like it flows toward low pressure. So if you watch it and you see the fluid is speeding up, that is a lower pressure part of the flow. So this works both in gas flows, but also in liquid flows to some extent. So if you see, right, I mean, we've seen this a little bit, but if you watch like fluid go from moving slowly to speeding up really fast, that means where it's going fast, the pressure has to be down because it's speeding up as it goes toward, as pressure goes down, right? It speeds up going toward low pressure. It's kind of getting like sucked in, going faster is maybe a different way to think about it. It gets sucked toward low pressure. The second direction that we can look at is this, not the streamwise direction, but the normal direction. So if we look at the normal direction n, we can write basically the same thing. So we can write v dv dn equals minus g dz dn minus 1 over rho d pressure dn. So if we again neglect gravity, this gives us the acceleration of the fluid in the normal direction is equal to minus 1 over rho d pressure dn. Right, or again, so acceleration in the normal direction is equal to minus 1 over rho d pressure dn. So this is acceleration in the normal direction, and this is the pressure gradient in the normal direction. So this one's a little bit harder to think about directly, but if we look at a curve, right? A curve is going to be, right? Our fluid particle is moving along a curve. As it moves along a curve in the streamline, another way to think about that is it's accelerating towards the center of that curve as it moves along, right? The velocity is changing direction. It's accelerating towards the center of that curve. So we have like a particle, say it looks like this, N and S. It's accelerating in the kind of the negative normal direction. So we have an accel to the center of the curve, which again is like out here, we would have, so this is our area of low pressure. That's our area of high pressure. So you can think about it like high pressure is pushing and kind of winning, and that's what's causing the acceleration. That's what's causing the curve. You get a low pressure at the center of a curve and a high pressure on the outside. So when you look at, say, streamlines like this, you can say right away without really knowing anything else, like this is a low pressure spot. This is a low pressure spot relative to the other pressures in the flow. And up here, like that's high pressure. This is high pressure, low pressure, low pressure. So you can get a sense of like how is the thing curving? That's related to what the pressures are. It's always going to curve around the low pressure areas of the flow. So the inside of a curve is going to be low pressure. The outside of the curve is going to be higher pressure. Or another way to think about it, like pressure goes up as you go this way. As you go out from the center of a curve, pressure is going to be increasing. To put a little bit more math to exactly what that looks like, the acceleration normal, that's going to be like, that's a curvature, so that's going to be a centripetal acceleration. This is a right, the centripetal accel, if you just look at the definition for a centripetal acceleration, sorry, it's minus v squared over r. So v, that's the velocity. R is the radius of curvature. So we can plug that into the equation that we had before. So we would have, right, if we plug that into to this equation up here, right, that would give us minus v squared over R equals minus 1 over rho d pressure dN, or V squared over R equals 1 over rho d pressure dN. So again, pressure is going to be, pressure increases in the outward normal direction. So you have a high pressure on the outside, low pressure on the inside. And it's going to be, again, it's going to be related to the radius of the curvature. So a tighter curve of the streamlines is going to be caused by larger pressure differences. If we go back to just to wrap up kind of our discussion for the day, if we go back to the streamwise direction, we can write that, so the velocity, d velocity ds minus g dz ds minus 1 over rho d pressure ds. So if we don't neglect gravity, sometimes we can't neglect gravity. We can rearrange this so with gravity not equal to 0 now, we can rearrange this to V plus G dz ds plus 1 over rho dPds equals 0. And this gives us a really cool equation. So this tells us about, we'll unpack it next time because I want to give you a chance to think about some of these things. But this tells us how fluids move along a streamline. And the cool thing is each of these terms, right, if one term increases, the other term has to decrease because they all have to be equal to 0. Yeah, Joey.
But when you keep writing this one over, is it like the density or is it S? Because up top it looks like S all the time. The one over S.
This is rho. So yeah, this guy, that, those are all density. Apologies for unclear writing. Yeah, I can see that. I'll make sure to close it. But no, I don't want that either. Density. Yeah, so this equation, we'll unpack this and we'll get it into a kind of happier form next time. But the cool thing about this is it's going to tell us about, okay, how do fluids move along a streamline? There's going to be a balance between these three terms, like a velocity, a velocity related term, a height related term, and a pressure related term. And these things are all going to have to balance as our fluid moves along streamlines. So if one goes up, the other goes down. If one goes down, the others have to go up to balance it out. So this will hopefully give us a little bit, I don't know, hopefully even this gives you some idea of the type of information that we can get about velocities, about pressure, about some of these concepts just from looking at at streamlines, especially when you combine this with other things that we know about them, like about the stream function. So if streamlines pinch together, that means velocity goes up. If velocity goes up, that means pressure. So all of these things are related. And there's really just like visually from looking at what the flow looks like, we can get a lot of information about pressures and velocities and yeah, kind of what's happening, at least at a qualitative level. And I think there's a lot of value to that. So what we're going to do for the rest of today's class is take out the, I think, in class number 6 or whatever you picked up today. For those of you online, it is posted on Moodle. And we're going to go through and try to, you guys all have heard like the simple explanation of how airplane wings work, right? The fluid's fast on the top and it's slow on the bottom, and that makes pressure and it causes lift. That's not totally wrong, but it's not quite that simple. So just go through and look at the flow around an airplane wing. Try to use some of these concepts, think through some of these concepts, look at the streamlines, and try to analyze for yourself like how you know that there's lift on this airplane wing, where the pressure difference is, how is velocity looking as you're kind of investigating this flow. So take the last 13 minutes, I guess, and we'll work on that, and I'll walk around and help you think through it or answer any questions that you might have.